Hello, dear students. Let us learn one more concept on, connected spaces, which is called locally connected spaces. Let us look at the definition, which says that a topological space X tau is locally connected if and only if for every point belonging to X, for every point small x belonging to the capital X, and for any open set G of that point X, there exists a connected open set G star such that X belongs to G star contained in G. Right? In other words, the family of all open connected sets, right, will form a base for some topology. For some topology. Okay, so remember what is a topology? What is a locally connected space? It's nothing but for every point belonging to X and an open set containing that point, there is always a connected open set in between. Connected open set G star in between the point and the open set. Okay, now we shall go to an example, and also we prove a theorem which says that locally connected doesn't imply connected. If it is locally connected, it need not be connected. We'll give an example. Example is this. Remember, we are proving this theorem. We are proving locally connected, right? Doesn't imply connected. Okay, yes. For example, let us consider discrete space. Let us consider discrete space. We'll prove discrete space is locally connected. So what is discrete space? Our tau is nothing but P of X. All the subsets of X are open, right? So all singletons are also open. And we know that singletons are nothing but connected, right? So any point belongs to the singleton X. X will belong to the singleton X, correct? For every X belonging to capital X. So if you have any open set of the small element X, there is always a singleton, right? See, X belongs to singleton X. This is obvious. And that is contained in the open set of G of X, right? And the singleton X is open and connected. See, for every point and for every open set of that point, there is always a singleton here, which is both open and connected. Therefore, discrete space is locally connected, right? So discrete space is locally connected. But if it has got more than one point, then it is not connected. If it contains more than one point, I can always have it as a separation. So if I take a discrete space having more than one point is not connected, but it is definitely locally connected. We have proved it is locally connected, but it is not connected. Hence, locally connected doesn't imply connected. Very, very important and very easy theorem. Now we shall go to one more theorem on locally connectedness. Okay. Every component of a locally connected space is open. We have to prove that every component of a locally connected space is open. We know what is component. Component is nothing but maximal connected set. Okay. So let C be a component of a locally connected space in X. So C is our maximal connected set in X, and X is locally connected. Okay, X is locally connected and C is component and C is subset of X. What we have to prove? We have to prove C is open. We are going to prove that C is neighborhood of each of its points. So take any point belonging to C. We want an open set in between X and C. We want an open set in between X and C. Let us see how we get that open set. Okay. So take X belonging to C, and C is definitely subset of X, right? So The element x will belong to capital X. Okay. And what is my x? X is locally connected. Locally connected. And this x is open set. Right. So you have any element belonging to the open set and x is locally connected. That means what? There exists an open and connected set containing x in between. In between. So x belongs to g of x contained in x, where this gx is open and gx is connected. Gx is connected. And what is C? C is maximal connected space. And this Gx is connected. And C is maximal connected. So Gx has to be contained in C. Gx has to be contained in C. And Gx, what is my Gx? Gx is both open and connected. So we'll take the open part here. So I got an open set in between X and C. Therefore, C is neighborhood of each of its points. Therefore, C is open. Hence the theorem.